As I mentioned yesterday, when we're dealing with categorical data, we have 3 different tests we want to use. First one we're going to see today, the goodness of fit test. If we collect data from 256 births uniformly across the year, we expect about 1/12 of them to occur under each of the zodiac signs. So, one for each month. That suggests about 21.3 births per sign. How closely do the observed numbers of births fit the simple null model? We have a specified model for the distribution and want to know whether it fits. There is no single parameter to estimate, so a confidence interval wouldn't make sense. A 1 proportion z-test won't work because we have a 12 hypothesized proportions, one for each sign. We need a test that considers all of them together and gives an overall idea of whether the observed distribution differs from the hypothesized one. Goodness of fit involves testing this hypothesis. So note, we can't use our prior test because we are dealing with a whole bunch of different proportions, one for each cell. Birth months may not be related to success as a CEO, but what about on the ball field? It has been proposed by some researchers that children who are the older ones in their class at school naturally perform better in sports than that of these children that get more coaching and encouragement. Could they make a difference in who makes it to the professional level in sports? So, I went out there and I asked ball players, what month were you born? And I went in and counted. So you can see here from month 1 to 12, I have these counts. And this is the national birth percentage. Now the first thing you need to do is to get your count totals and multiply them to what the expected percentage is. So 0.08. That's where I get my expected values that I should have. Right here. So this is pretty much what you were expected to have on the ball field. So I have both the observed, the data I collected, and the expected. 2 different charts. Now what we're going to do is enter both of these values into our calculator. So go step 1, stats, edit, and enter the observed values in L1 and the expected values in L2. So everything here and here goes into L1. And then these values will go into L2. L1 is your countable, L2 is your expected values. Drug dog.
They had to come 420, huh?
Is it?
Yeah.
That is funny.
Do the dogs smell to the doors?
Gee, I'm surprised in old school they brought dogs in the classroom.
Oh.
Next thing you know, it was more so me. I was like,
I've never been in a class where they actually came in.
No, old school, they used to like come to class and pass them by the benefits.
That sounds.
Nobody ever had anything on.
Can they come back?
Do they smell pens?
I think you should be worried about your students, Mr.
I think so too.
Clark.
I think we should have another community time on vape pens. Can't have too many of those apparently. What they should do is show pictures of what people's faces look like after those pens explode. Because they are made by the cheapest buyer. Yes, if you haven't guessed so far, categorical data has a lot more information you got to punch in and calculate than quantitative data.
Yeah, we can tell. Nice. Okay.
Is it really 420?
Yeah.
Yeah.
Are you sure? Oh, there it is, right there.
That's the dogs.
That's funny.
You can tell. Oh, yeah. Look at that there.
All right. I should have taken a picture of that. Sent it to my wife. Or
It's not
post it
gonna
on
come
Facebook.
back.
Okay. Now that we entered that into our table, let's make sure our assumptions are met. Are ball players more likely to be born in some months other than others? We have observed and expected counts for the 1,478 players born since 1975. So are the assumptions and conditions met to perform a goodness of fit test? So remember, counted data condition. I have a month-by-month count of ball players' births. So yes, my data is countable, right? I'm not using any proportions or percentages. Independence assumption. These births are independent from one another. That makes sense. Randomization condition. Although they are not a random sample, we can take these players to be representative of players past and future. 10% condition. These 1,478 players are less than 10% of the population of 16,804 players who have ever played Major League Baseball. So we meet that condition. And expected cell frequency condition. The expected counts exceed are greater than 5. So as I look here, go back, oops. Each of these are greater than 5, right? I don't have any of these values less than 5. So I meet that condition. So you're looking at the red here. Those numbers need to be more than 5. If not, have some more surveys or go and talk to some more people. What are the hypotheses and what does the test show? So my null is going to be the distribution of births for Major League players is the same for that of the general population. Meaning my alternative is that it differs from the rest of the population. That ball players are expected to be in 1 month more than another based on the general population. Now the first thing you need to calculate is the degree of freedom. That is required with our calculator. What that is the number of cells minus 1. So I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. One for each month. So I have 12 cells minus 1. So my degree of freedom is going to be 11. Now let's test a goodness of fit test. Guess what? It's in the calculator.
Yes.
So go to stat test all the way down to D and you see our chi squared, GOF. What do you think that stands for?
Goodness of fit.
Good job. Goodness of fit. And hit enter. You'll see you want your observed to be an L1, expect an L2, just like we did. And DF, our degrees of freedom was 11. Go down to calculate, and you'll get what's your p-value. Our p-value is very, very small. Do I reject or fail to reject?
Reject.
Since it's less than 0.05, I am going to reject the null. So there is evidence that birth months of Major League players have a different distribution from the rest of us. Interesting. So this is how we're going to test goodness of fit. Stat. Test. But first, like I mentioned, we must make sure we have all our observed values in L1 and expected values in L2. So let me have you give this one a try. We have counts of 256 executives and 12 zodiac sign categories. The natural null hypothesis of that is that birthdays of executives are divided equally among all zodiac signs. Question, are CEOs more likely to be born under one zodiac sign than others? So 1 month more than another? My null, births are uniform, distributed across the zodiac signs, so they're evenly distributed. My alternative, births are not uniformly distributed, so there might be 1 month that I see them more than another. I went ahead and put our table here. Here's our observed values. Where are you going to put this in?
In the L1.
L1. And my expected?
L2.
L2. And then calculate the goodness of fit and determine whether or not you reject or fail to reject the null.
But not for me.
I hope you first checked your conditions. So the counting data condition, yes, I have counts of the number of executives in each 12 month. Independent assumption, the birthdays of executives should be independent from each other. It'd be kind of weird if it wasn't. Randomization condition, this is a convenient sample of executives. It is random. but not a SRS, simple random sample. However, there is no reason to suspect bias. And do I meet the expected cell frequency condition? These are greater than 5, so I'm good to go. Next, I need to calculate my degrees of freedom, 12 months, 12 cells, minus 1. My DF is 11. Now I have enough information to go to my calculator, and you should have got a p-value of this, right? 0.93. Pretty big. So do you reject the null or fail to reject the null? I fail to reject the null. P-value of 0.926 says that if the zodiac signs of executives were in fact distributed uniformly, an observed chi-squared value of 5.09 or higher would occur about 93% of the time. This certainly isn't unusual, so I fail to reject the null hypothesis and conclude that these data show virtually no evidence that executives are more likely to have certain zodiac signs in other months. And if we look at the table, it is pretty close. Fairly close there. You can almost visually see that there's no evidence. Now, if you were to do this by hand, here would be our formula. We need to take the sum of all cells with the observed minus the expected squared divided by the expected value. So here's a table you enter in the calculator. Now what you would do is subtract the observed from the expected. That would get your what's called the residual. Then square it, and then divide that by the expected, and then add up all these values together. So this, you're going to get a value for each cell, add those up, and that's going to give you that chi-squared value. Aren't you glad you have a calculator to do all that for you? Here's how you would do it by hand. Now, when we calculate our chi-squared for the zodiac sign example, we got 5.094. That value would be a big number for z or t, leading us to reject the null hypothesis. But not here though. What is a big value for that x squared? Think about how x squared is calculated. In every cell, any deviation from the expected count contributes to this sum. So notice I'm gradually adding more and more deviation. Large deviations contribute more, but if there are a lot of cells, even small deviations can add up. For x squared, the decision about how big is big depends on the number of degrees of freedom. So we calculate our degrees of freedom as 11. My chi-squared is 5. It's not bigger than that value, so I would say that is not a very big distribution. The previous one, we got a very big distribution, right? So you may have to go back and explain why, or take more surveys. Here's the big trouble with the goodness of fit test. They are more likely to be performed by people who have a theory of what the proportions should be in each category, and who believe their theory would be true. Unfortunately, the only null hypothesis available for goodness of fit test is that the theory is true. And as we know, the hypothesis test procedure allows us to only reject a null or fail to reject a null. We can never confirm that a theory is in fact true. So with this goodness of fit, we can never prove something, but we can disprove it. That would be the point of doing it.